Today, the most advanced and luxurious touring motorcycle available is the Honda GL 1500 Goldwing. If you've attended Honda's Update 88 clinic, you learned a little about how the 1500's induction control systems work. This program will give you a deeper look into each one. There are 7 separate systems on the 1500. It may take a little effort to understand them all, but by the time you finish this program, you'll know how each system works and when. Understanding the operation of the induction control systems will help you diagnose the systems faster and get to the solution. These computer-assisted dual downdraft CV carburetors are the center of the induction control system. After viewing this program, you'll be able to name the parts of each induction control system, and you'll be able to identify how each system functions under specific conditions. We'll show you how the intake hot air system and the heated intake manifolds and carbs help the motorcycle pull smoothly when the engine is cold or in cold weather. You'll see how the air jets are computer adjusted to suit load and speed, how the mixture is compensated for high altitude, and how the accelerator pump compensates for cold weather operation. You'll see how shot air dilutes the rich mixture after the throttle is closed, and finally how the secondary air system reduces HC and CO emissions. Now that we've covered the general function of each system, let's get into the details. The intake hot air system improves throttle response, power, and drivability in cold weather. When the outside air temperature is below about 55 degrees Fahrenheit, preheated air from the left exhaust manifold is added to keep intake air warm. On this mock-up of all the systems, you can see that manifold vacuum passes through a one-way valve to this vacuum actuator, which controls a flap door. Vacuum is also teed to this bimetallic valve. Did you notice? All the hoses in this system are color-coded with pink bands. Each hose is also numbered, corresponding to service manual diagrams. The color codes within a system are the same, but the hose numbers are different. It is possible to have numbers duplicated on other systems, so the hose colors are especially important. It may not seem important now, but when you're working on a dressed Goldwing, these color codes and the hose numbers will help you identify hoses quickly. Here's how the system works. When there is no vacuum in the actuator, a spring in the actuator closes the flap door, blocking the hot air passage, so only outside air enters the air cleaner. Then, when vacuum is applied through the one-way valve, the actuator opens the flap door, sending preheated air to the carburetors. Without the one-way valve, the flap door would simply open and close as manifold vacuum rose and fell. The one-way valve works like a vacuum stabilizer. Rather than being just for cold start, the system comes into play whenever air temperature at the carb inlet drops below approximately 55 degrees. The real key to the intake hot air system is the bimetallic air bleed valve. The bleed valve regulates the position of the hot air flap door to keep air temperature at the carb inlet near ideal. While the engine is running, it will open or close the hot air flap door as much as necessary to achieve the correct temperature at the carb inlet. That's how the system works. And here's where the key parts are on the motorcycle. The bimetallic valve is under the air cleaner element, and the actuator controls this flap door in the air inlet tract. Notice the pink color band on the hose. It leads to the one-way valve, which is just under the base of the air cleaner. Now let's back up a little. Suppose you've been driving 1.5 hours. The coolant temperature is normal, and the outside air temperature is 45 degrees. Would preheated air be fed to the engine? Let's look at the system again. Yes, it would. Even with a warm engine, the cold air would keep the bimetallic valve closed, so the flap door would be held open by manifold vacuum. The second temperature control is the heated intake manifolds and carbs. To keep fuel atomized at low temperatures and to prevent carburetor icing, the intake manifolds and carburetors are warmed by engine coolant, controlled by this thermovalve. Here's how it works. When the engine is cold, the thermovalve is open. Warm coolant flows from the hot cylinder heads through the carburetor manifolds and carburetor base before returning to the radiator. Then, when the coolant reaches about 170 degrees, the thermovalve closes, letting the coolant bypass the manifolds and carbs, returning directly to the radiator. This keeps the manifold and carbs from getting too hot. This thermovalve is the heart of the system. It's not easy to get to, but it's more trouble-free than any thermostat. Consider another situation now. Suppose the air temperature is 40 degrees, and you've just ridden 150 miles. You stop for a few minutes. When you restart the engine, would the thermovalve be open or closed? It would be closed. Because the engine coolant would still be hot, the thermovalve would be closed, bypassing the manifolds and carbs. The air-fuel mixture controls on the GL 1500 are computer controlled. Their job isn't very different from that of a fuel injection system, but they work a little simpler. This carburetor control unit makes it all happen. It adjusts the amount of air flowing to the primary main air jets through this air filter by opening and closing solenoids AJ2 and AJ3. The hoses have white bands on this system. The carburetor control unit adjusts the amount of air flowing to the primary main air jets, depending on several inputs. It monitors a direct input from the TA, or air temperature sensor, as well as inputs from the ignition control unit, for engine RPM from the pulse generator, and manifold vacuum from the PB sensor. This fine-tuning of the air-fuel mixture is just what a fuel injection system does. But instead of varying the amount of fuel, the GL 1500 varies the amount of air passing through the computer-controlled air jets. A fixed primary main air jet 1, is used for basic metering. The carburetor control unit activates solenoids AJ2 and AJ3 to lean or richen the mixture via air jets 2 and 3 when directed by the ignition control unit. This allows the system to compensate for changes in air temperature, RPM, and engine load. The carburetor control unit opens and closes one or both of these solenoids as riding conditions demand. Both closed is full rich, while both open is full lean. Here's the ignition control unit. It receives information from 3 sources. On the front of the crankshaft, the pulse generator sends an RPM signal. Just below the tachometer, air temperature is measured by the TA sensor. And inside the ignition control unit, manifold vacuum is measured by the PB sensor. Using this information, the ignition control unit tells the carburetor control unit when to turn solenoids AJ2 and 3 on and off to match any riding condition. The service manual does tell you how to check out AJ2 and AJ3 and the carburetor control unit, Plus, it has a troubleshooting chart that leads you to the cause of a problem without guesswork. It may save you time and money. Working alongside the computerized air jet control system is the high-altitude compensation system. That's why both systems' hoses are color-coded white. The high-altitude system also adds air to the primary main air jets and the slow jets. It's mechanically operated by this air jet controller. At sea level, or up to about 3,000 feet, this system is inactive. But above that, a sealed bellows, or aneroid, inside the air jet controller begins to expand. The aneroid is filled with air at sea level atmospheric pressure. So at higher altitudes, the aneroid expands. It slowly opens valves that allow extra filtered air to lean both the slow speed and the primary main circuits in both carburetors. By the time you reach 5,000 feet, the aneroid is fully expanded for maximum high-altitude compensation. Then, as altitude decreases, the air jet controller slowly closes its valves, enriching the mixture as you drop below 3,000 feet. The air jet controller is in the right fairing pocket. It sends a small amount of air to the carburetors through these white banded hoses. It has its own internal air filter which doesn't require service. So, why are there two different control systems with the white banded hoses? Both the computerized air jet control system and the high altitude compensation system lean the air-fuel mixture by adding extra air. Just say to yourself, white means air. Now, suppose you're riding up a mountain road. You stop at 4,500 feet. What will the air jet controller do as you continue to climb? It'll open some more until about 5,000 feet when it's wide open. This gradual mixture leaning means you'll have less power loss at high altitudes. The next system we'll look at is the temperature compensating accelerator pump. Normally, the volume of fuel injected by the accelerator pump is fixed, regardless of temperature. But the GL 1500's pump varies the amount of fuel injected, depending on fuel temperature. In the bottom of the pump housing is a bimetallic valve. It's immersed in the fuel, and it opens above approximately 50 degrees Fahrenheit. Here, part of the fuel circulates through a bypass port, back to the feed side of the pump. Then, when fuel temperature drops below about 50 degrees, the bimetallic valve slowly closes. So more accelerator pump output is injected into the carburetor bores. When the accelerator pump valve closes, it doubles the output. But since the increase is only from 0.45 to 0.9 cc's, it's a little hard to measure. You can only check it by observation. But the pump volume does increase when cold. When the throttles are closed, there is residual fuel on the walls of the intake manifold. To dilute this mixture, the GL 1500 uses a shot air system, which allows filtered air into the intake manifolds. The system is built around this shot air valve and two solenoids. Solenoid SA is controlled by the carburetor control unit, and solenoid N is controlled by the gear position switch. All these system hoses are coated yellow and allow filtered air into the intake manifold. The diaphragm chamber within the shot air valve contains a small orifice which connects both sides of the diaphragm. During idle or cruise, vacuum is equal on both sides, so the valve is closed. During acceleration, the vacuum above the diaphragm is higher, so the valve remains closed. But during decel, The vacuum below the diaphragm is higher than above it, so the valve opens. This lets some filtered air enter the intake manifold. The opening duration is 2.5 seconds, the time it takes for vacuum to equalize on either side of the diaphragm. The amount of added air is limited by a restricting orifice in yellow hose number 7. Above about 1900 RPM, the ignition control unit signals the carburetor control unit to open solenoid SA. So additional air passes into the intake manifold. Solenoid N plays a different role. Since shot air is not necessary in neutral, solenoid N keeps the shot air valve from opening. So in neutral, the gear position switch opens solenoid N, applying manifold vacuum to the other side of the shot air diaphragm. This keeps the valve from opening. Here is the shot air valve. The solenoid SA in the left fairing pocket, and solenoid N, located directly below the coolant reserve tank. Now, just suppose you were accelerating at about 4,000 RPM in second gear when traffic suddenly stops. In the interest of safety, you suddenly close the throttle. What would the shot air system do? Since engine speed was well over 1900 RPM when you began decelerating, pulse generator signals to the ignition and carburetor control units would have already opened solenoid valve SA. This would now add maximum air to the intake manifold because air would pass through both hoses 6 and 7. Last, let's look at the secondary air system. It adds filtered air at the exhaust ports while cruising, reducing HC and CO emissions. The key parts are these two sets of reed valves. The secondary air valve and the control valve. The system is strictly vacuum powered and all the system hoses are coded green. Here's how it works. Just upstream of the exhaust ports are two banks of 3 reed valves. The reeds open when there is a brief instant of negative pressure at the exhaust port, allowing some fresh air to enter the exhaust system. During decel, increasing manifold vacuum opens the control valve, which in turn gradually closes the secondary air valve. When manifold vacuum is highest, no secondary air can pass into the exhaust ports. If it did, the super lean mixture could cause afterburn. This altitude sensing aneroid in the control valve adjusts the point at which the valve starts to open. So again, the amount of secondary air added is variable according to the intake manifold vacuum plus altitude. The reed valve banks are under the intake manifolds. The secondary air valve is underneath the carburetors, and the control valve is here. Okay, a quick review. When you're decelerating, is air passing through the reed valves into the exhaust? No, because high manifold vacuum closes the secondary air valve. So airflow to the reed valves is shut off. All right, you've seen how each of the 7 GL 1500 induction control systems work and when. You should be able to name their key parts. There's a lot to remember about these 7 systems. So here's a little help. The system's diagrams complement the service manual and provide page references. We've presented a lot of information here. So if you're not really sure about how any of the 7 systems work, go back and watch that segment again.